Welcome to the next lecture of sinusoidal of circuit analysis 2, in which we are going to see the steady state analysis of the sinusoidal circuits with sinusoidal forcing function. In this lesson, we are going to see the implementation of different analysis techniques, for example, nodal analysis, mesh analysis, Thevenin theorem, superposition theorem, Norton theorem, and source transformation techniques. And mainly we would be discussing all these techniques based on our previous knowledge in electric circuit analysis 1, where we have studied all these techniques for DC analysis also. So here we will be solving the examples and try to look into the differences while working with AC circuits. So in AC circuit analysis, we usually have three different steps. First of all, we try to transform the circuit into its phasor or frequency domain, and then we solve the problems using any of the mentioned techniques. And this step is almost similar to the to our previous DC analysis, circuit analysis techniques, except we are working with complex numbers due to phasors here. And finally, we transform our phasor domain, our frequency domain results back into the time domain. So there is an additional step of transforming the time domain into frequency domain and then transforming back from frequency domain to the time domain as well. So in this way, we would be able to solve the AC circuits in our today's lecture. So starting with the nodal analysis, the basis of nodal analysis is KCL, Kirchhoff's current law, and because we have already seen in our previous lectures that KCL is equally valid in phasor domain as well, so we can use it for analyzing AC circuits. Consider this example where we are asked to find I of x in the circuit given here. So in this circuit, we have been given a resistance, capacitance, and inductance. In fact, two inductances, an independent current, and dependent current source, and independent voltage source. So as the first step, we need to transform these time domains circuits into the frequency domain. So this is what we are going to do. In the frequency domain equivalent or phasor domain equivalent of this voltage source would be 20 angle of 0, because there is no phase angle mentioned here. Omega is 4 in this case. So this is what we have written here. Secondly, for this 1 Henry inductor, we already know that the impedance of the inductor, or most specifically the reactance of the inductor, is J times omega times L. So we have already seen that omega is 4 here. So its reactance would be J times omega times L is J times 4. For another inductor of 0.5 Henry, J omega L would be J times 2. And for 0.1 farad capacitor, the reactance can be found using this relationship 1 upon j omega c, which will result into minus j 2.5. So our equivalent circuit would be like this one, where we have written all these quantities in phasor domain. All the reactances are mentioned and the voltage sources are converted into phasor domain. We have already now converted our this time domain current into phasor domain current as well, and this is the current from this capacitor branch. So applying KCL at node 1, we have this node 1 and this node 2 here. So at node 1 we apply KCL, and current entering the node should be equal to current leaving the node, or sum of all the currents at a node are equal to 0. So in this way, when we put all the values like before, what we get is this equation: 11v1 plus 15v2 is equal to 0. Equation 10.1.1 and 10.1.2 can be put in matrix form. So in order to solve for V1 and V2, we need to solve these two simultaneous equations because we are operating in frequency domain. So these are mostly the linear equations. So we are going to solve them by this Cramer's rule sort of thing, and ultimately we reach the conclusion that V1 is 18.97 angle 18.43 and V2 is 13.91 angle 198.3. So as a first step, what we did, we transformed time domain quantities into phasor domain quantities. Then we solved using similar method. However, we have uh, put our concentration on the point that these are complex numbers, so wherever necessary we need to handle them with care so that we do not make any mistakes and we do not treat these numbers as just real numbers. These are phasor quantities and these can include the magnitude and phase angle as well. So here we have got the magnitude and phase angles. So in this way, while if we want to, we have to find the current through the capacitor. So capacitor's voltage divided by the capacitor's reactance. So this would result into 7.59 angle 108.4 as the angle of the as the phasor current through capacitor. And when we convert back it into the time domain, the amplitude would be 7.59 cosine of 4t, 4 because we have already seen in start that omega is 4, and plus theta, and theta would be 108.4. This is what we can write in time domain. So in this way, we have now converted as a last step from the phase domain to the time domain. Next, we see another example of the nodal analysis. In this example, we are given with the supernode. Compute V1 and V2 in the circuit of figure 10.4. This is figure 10.4, and we can see that there is a voltage source between two nodes. So this would make the supernode. So V1 and V2 and any components in between these two would make the supernode. So here we can see that node 1 and node 2 form a supernode as shown in figure 10.5, this one. So applying KCL at supernode. So in order to solve this circuit, we would take this as a single node. However, the one terminal is at V2 and other portion is at V1. So writing the equation for this supernode would be 3 ampere current is entering this node, and the current V1 upon minus 3J would be leaving, and these two currents would also be leaving, which can be written as V2 divided by the impedance J6 and V2 divided by resistance 12. So these will make the equation like this one. So as this is a super node, we will treat this as single node and we will write a single equation for this. This is what we have seen in our previous course, Electric Circuit Analysis 1 for DC circuits. So now this equation can be simplified like this one. And secondly, we will write the equation for this supernode as well. So equation of supernode would be that V1 is equal to V2 angle 1045, 10 a magnitude angle 45. This is what the potential difference between V1 and V2. V1 is at higher potential, the positive terminal, V2 is at lower potential, so V1 minus V2 would be equal to 10.45, and because this resistance is in parallel to this, so obviously we can say that the same voltage is appearing across this 4 ohm resistance as well. So the equation of this supernode would be V1 minus V2 is equal to 10 angle 45. This is what we can see from this equation. So now we have two variables V1 and V2, and we have got two equations, one from the supernode and other from the circuit with supernode. Now solving these two equations, we can find V1 and V2 like this one. V2 is this one and V1 is equal to this one. And if required, because in the question we were given that we need to find this phasor voltage at node 1 and 2. So we are not converting it back to the time domain. If we are asked to find the time domain quantities, then we can easily convert them into time domain. However, we do not know the operating frequency omega here, so we would write omega in the time domain as well. So next we move on to the mesh analysis. Mesh analysis is based on the KVL, and as KVL is equally valid for the phasors, we have seen already in our previous lecture. So we can see we can solve this circuit with we can solve AC circuits with mesh analysis techniques also. So one thing one should keep in mind is that the very nature of using mesh analysis is that it is to be applied to the planar circuits. So we have the planar circuits, and we have already seen the details in our previous lectures, previous course lectures. Planar circuits are those which can be as a simple uh, explanation represented in two-dimensional plane in fact. The determine current I naught in figure 10.7, right? So this is I naught, and we need to find this one. So we have three um, loops here, three mesh here, I1, I2, and I3. I1, 2, and I3, and we need to find I naught. Applying KVL to mesh 1 would result into 8 ohms plus J times 10 ohms minus 2J. This is direct method of applying KVL. We could write 8 I1 10J times I1 minus I3 and minus J2 times I1 minus I2. And this is the simplified form of this equation. So for mesh 2, for example, we could write the current through this capacitor is I2 minus I3, and voltage drop across it would be I2 minus I3 times minus J2, and the voltage drop across this impedance, capacitive impedance, would be I2 minus I1 times minus J2. Similarly, the voltage drop across this one would be 4 times I2, and this is voltage source itself. So in this way we can write the equation like this one simply. For mesh 3, I3 is 5 ohm because this is a current source and it is not a shared kind of current source between two loops. It is only appearing in this I3 loop. For example, if this voltage, this current source appears like here, then we will make a super mesh by combining these two meshes, these two loops, as you will see shortly. So here I3 is directly equal to 5 angle 0. So now solving these three equations, this one, and I3 is equal to 5, we can simply find I1 and I2, and our I naught is minus I naught, I2. I naught is nothing but the current flowing in opposite direction to I2 of equal magnitude. Or we can say that I naught is the opposite of I2, that is opposite in phase and same in magnitude also. And here we can find this one. This is I2 and I naught is minus of I2. Because we have this negative angle here, we just transformed the angle and written positive here. We could simply write I2 is equal to minus 6.12 angle minus 35.22 as I naught. I naught is equal to minus 6.12 angle minus 35.22 is similar as 6.12 angle 144.78. So now coming to the next example where we have got this current source in between two meshes. So we have to write the equations as figure 10, mesh 3 and 4 form a super mesh due to the current source in between. 3 and 4 are these meshes. So we can write the equation for the mesh like this one: minus 10 plus 8 minus 2i. Sorry, this is equation for mesh 1, and this is mesh 1, as we can see from here. So writing the equation for mesh 1 is minus 10, this voltage source, the voltage drop across this one, plus voltage drop across this one, this capacitor. So in this way we can simply write this equation. For equation mesh 2, we can write from here that I2 is minus I3 because our I2 direction is like this one and I3 is opposite to that. So we have just written this one like this. And for super mesh, this is the super mesh. This is the super mesh which comprises of I3 and I4. So we can write the equation like this one. Current I3 is flowing through here, minus 4j times I3, 6 ohms times I4, 5j times I4 minus I2, 8 times I3 minus I1. Like this, and rearranging this equation, we can get this equation. And also, this current source appears between two mesh I3 and I4. So, and this current would be the I3 current. I3 current is flowing like this one. This is I3 and this is I4. So, difference of I4 minus I3 is equal to 4 angle 0. I4 minus I3 is equal to 4, and we are taking I4 minus I3 instead of I3 minus I4 because the direction given by this current source is same as the direction of I4. So we assume that I4 is greater than I3. So in order to get the similar direction, we take I4 minus I3. If we take I3 minus I4, then we suppose that I3 is bigger than I4, or we suppose that this direction is not true. So in order to solve that, we can write I3 minus I4 is equal to minus 4 angle 0. This is also true, but a simplified form is this one. So now we have got these four equations: I1, I2, I3, and I4 are the four variables. We have got four equations and we can solve them simultaneously in order to get the solution. So first method can be the Kramer rule type of thing, and second method is MATLAB based, and we are not going to discuss it here. So solving these equations, we will get the voltage and current in respective loops and nodes. Superposition theorem. Superposition theorem is a circuit analysis technique. Since AC circuits are linear, the superposition theorem applies to AC circuits the same way it happens to the DC circuits. So for linear circuits, as I mentioned earlier, the circuit equations we are getting are linear. We are solving them with the linear methods of solution, solving the circuit. So the theorem becomes important if the circuit has source operating at different frequencies. Superposition theorem. We have already discussed in detail that when working in phasor domain, we suppose that all the frequencies are similar, or conversely, we can say that frequencies of all the sources present in a circuit are similar. For example, in this circuit, we have these three sources, two current sources and a voltage source. So the frequency of this current source and this voltage source all are similar. That is why they are converted into phasor domain and operated simultaneously. However, if there is a case when we have multiple frequency sources here, let's say current 1 source is at omega 1 and current 2 source is at omega 2, then we cannot add their responses. And in that case, superposition theorem becomes important, and we will see shortly that these sources will result into different subparts of the circuit. In this case, since the impedances depend upon the frequency, impedance due to source 1 I1, as I mentioned earlier, would be different because j omega L would be j times omega 1 times L, and if the frequency of the other source is omega 2, then the impedance offered by same inductor to that voltage or current source would be different because of the difference in the omega. That is why we are saying that we will get two different sub-circuits from the single circuit having multiple or two different frequencies. And total response would be obtained by adding the individual responses in time domain. We cannot add them in frequency domain. We have discussed in very detail in our previous lectures. It is incorrect to try to add the responses in phasor domain, and because of this factor j omega t, for one quantity it's omega 1, for other source it's omega 2, and we cannot directly add them, therefore we need to convert it into time domain. So for the sake of convenience, we consider all the sources operating at similar frequency, and if they are at different frequency, we need to add the responses in time domain. So as an example, we solve this circuit of superposition. Here we have three different loops, I1, I2, and I3, and we intend to solve this for I0. This is the same example as we did previously for the KCL. So in order to find this current, we need to get the response of the current due to different functions, different forcing function, I would say. Let us say the first of the forcing function is this, and other forcing function is this one. So how will it work? I naught prime and I naught double prime are due to the voltage and current source respectively. I naught prime is due to this one, and I naught double prime is due to this current source. So first we short circuit, let us say, in order to find I naught prime, we need to open circuit this one, the current source, and the circuit would be solved for due to this voltage source. And secondly, for in order to find I naught double prime, we will be considering this source, and this voltage source will be short circuited. The first case is like this one. Now we need to these two resistances are in series in parallel to this impedance, and then these two are in series, so the resultant of these is in series with this one, so we can find or we can calculate I naught prime from these simple voltage divider or current is equal to volt upon R or impedance X. So in this way we can find this, we can solve this circuit for I naught prime. Secondly, when we consider this voltage source as a short circuit and we only consider the impact of this current source, in order to find I naught double prime, we can solve the circuit like this one. So this is not compulsory to solve with by just transforming the equivalent parallel combinations of the circuits. We can use KCL or KVL or mesh analysis or nodal analysis, any of the techniques to solve this type of circuits. So in simple words, our objective should be clear that we need to open circuit all the current sources and consider one of the voltage source. And if we have to consider the current source, we need to short circuit the voltage source and any other open circuit any other current sources in the circuit. So in simple words, we find the impact of this current in this branch, and it is treated as or termed as I naught double prime. In the end, we will add I naught prime and I naught double prime to get I naught. So this is what we have done here. I'm not detailing its mathematical steps because we have seen these many times before this one. So as I mentioned earlier, this is the example we have already solved previously with different analysis technique. We are reaching the same conclusion, we are reaching the same response. It should be noted that applying superposition theorem is not the best way to solve this problem because when we are solving this problem with superposition theorem, we have seen that our calculations and our steps are getting longer. So it was not a good option to solve this circuit with superposition theorem. However, we can see that there are some of the circuits and options which can be easier to solve with superposition theorem than any other method, like this example. In this example, what we are going to do is we are going to solve for V naught, the voltage across this 1 ohm resistance, using superposition theorem. So here what we need to do is first we need to understand that this V naught would be the sum of the response due to this voltage source, this current source, and this voltage source. So these three components, these three sources should be treated one by one. And what is the basic principle? The basic principle is that when we consider this voltage source, we need to open circuit this current source and short circuit this voltage source. When we are considering this current source, we will short circuit both these voltage sources. And we can then consider this voltage source, 5 volt voltage source, and at that time we will open this current source and short circuit this voltage source. So in this way, calculating, getting the response one by one, and by adding them in the end, we will get V naught. Solving this circuit with any other technique would be a bit messy because it contains both the voltage and current source. If we try to solve them, we need to go into some details of super mesh or super node also. We may need to solve them with them. So this is all about this one. Here we have just short circuited this voltage source, open circuited this current source, and we are considering only 5 volt source. Then we have short circuited this one, we have open circuited the current source here and only considering this voltage source. And finally, we are considering this current source and we have short circuited the voltage source here. So this only inductor, 2 Henry inductor would be in parallel to this, and if it is short circuit, this 4 ohm resistance and zero point 0.1 farad capacitor would be in parallel, as we can see here. So in the end we have added all these responses and found the overall response of the circuit across 1 ohm resistance, like this one. This is all for today. We will meet in our next lecture and see how the source transformation works, and other techniques will be seen in the next lecture. Thank you very much.